Question 2.67. A solid non-conducting sphere of radius A has a total charge plus Q uniformly distributed throughout its volume. The surface of the sphere is coated with a very thin, negligible thickness conducting layer of gold. A total charge of minus 2Q is placed on this conducting layer. Use Gauss's law to do the following. In part A, we have to find electric field for region R less than A, which is inside the sphere up to and excluding the gold layer. So for the first part of the question, we need to find what would be electric field at a distance R, which is inside the sphere up to but excluding the gold layer. So we can choose the distance R to be here to construct the Gaussian surface. I will call this radius R. Radius R starts from center and it can go up to the gold layer but excluding it. And we need to find what would be electric field in these regions. We know from Gauss's law integral E dot dA is equal to charge enclosed over epsilon naught. Charge enclosed is the total charge within the Gaussian surface, and we can find this charge enclosed by taking differential charge dq, because this charge will change as the radius or the distance from the center changes. So I can write dq as rho times dv, where rho is the charge density of the sphere and dv is the differential volume. So we write this as rho times surface area 4 pi r squared into dr, because volume can be written as area into the length. The length or the radius of the sphere is changing as you go away from the center, so we keep it as dr. I can find the total charge by integrating dq from 0 to the point r. So charge enclosed will be equal to integral dq going from 0 to r, which will be equal to integral rho 4 pi r squared into dr. Rho and 4 pi are constant. You can take them out. Rho 4 pi integral 0 to r squared into dr. Integral of r squared will be r cubed by 3. So you get this as rho 4 pi r cubed by 3 going from 0 to r. Substitute the limits and you will get charge enclosed to be equal to rho 4 pi by 3 r cubed. Now rho is the charge density of the sphere, the total charge density. And you can calculate the total charge density rho by taking charge, the total charge Q, which is positive Q over here, over the volume of the entire sphere, total volume. So this will become capital Q over 4 by 3 pi AQ. AQ because A is the radius of the sphere. So I will substitute for rho here. You get this as capital Q over 4 by 3 pi AQ into 4 pi by 3 r cube. Cancel off the common terms and you get the charge enclosed to be equal to capital Q r cube over a cube. Now we can use this value of charge enclosed in our first equation of Gauss's law. So let's substitute this in Gauss's law. Integral E dot dA I can write as just E into A equals charge enclosed, which is Q r cube over A cube into epsilon naught. Then to find E, we divide by the area. Surface area of the sphere is 4 pi r squared. So we will substitute that. I write E equals Q r cube over divide by the area 4 pi r squared into A cube epsilon naught. Cancel the common terms, r squared and r cube will cancel, leaving with Q r over 4 pi A cube epsilon naught. So this is how you can calculate electric field due to a non-conducting sphere in region inside the sphere. And if I were to write this in vector form, we will write electric field E bar equals Q r r cap over 4 pi A cube epsilon naught. The electric field is pointing radially outward. Now this electric field is directly proportional to R. So if you were to plot a graph of electric field versus the distance R from the center, electric field value will keep on increasing until you reach the radius A. Next we discuss part B. Find electric field ER for R greater than A, outside the coated sphere, beyond the sphere and the gold layer. So now we need to find electric field outside the sphere, beyond the coated gold layers. So I will construct my Gaussian surface outside the sphere at a distance R, which goes beyond the gold layer. Let this be R. I need to find electric field at this point. So again, let's start with Gauss's law. According to Gauss's law, integral E dot dA is equal to charge enclosed over epsilon naught. Integral E dot dA we can write as E into A. Charge enclosed is the total charge enclosed by the sphere and the gold layer. So the charge on the sphere is plus Q. Charge on the gold layer is minus 2Q over epsilon naught. To find electric field, I will just divide by the area. So E becomes equal to Q minus 2Q will be minus Q over A times epsilon naught. That gives me electric field as minus Q over surface area of the sphere is 4 pi r squared epsilon naught. So this is electric field outside the sphere when you include the gold layer. In part C, they want you to sketch a graph of E versus R and comment on the continuity or discontinuity of electric field and relate this to the surface charge distribution on the gold layer. So now we need to plot a graph of E versus R, both for the cases which were inside and outside. So I'm going to just draw axis. This is distance R. Electric field here is positive and here it's negative because in case B it becomes negative. Let this be the radius of the sphere A. As discussed in part A, electric field E was positive Q R over 4 pi AQ, which shows that electric field is directly proportional to R in region inside the sphere. So I will draw a straight line. Then as you go outside the sphere, electric field becomes negative. So this is the point of discontinuity. Here electric field becomes negative and is inversely proportional to R squared. So it will vary as 1 by R squared as you go away from the sphere. So it decreases. The value of electric field at this point would be QR over 4 pi AQ. And the value of electric field at this point will be minus Q over 4 pi R squared epsilon naught. So there is a discontinuity at the surface charge distribution where you have the gold layer. The presence of gold layer causes a sudden spike in charge, and thus you have this discontinuity.